Hello, this is Paragus. Welcome to Tech Capsule. In today's capsule, we are going to check out the operation of a rectifier. So this is one of the major application of power electronic converters or power electronic devices or switches. A device which converts AC to DC is called as a rectifier. So we have the input coming as an AC and the output required is DC. So here we are going to talk about a full wave rectifier. The full wave rectifier would be a one which would be converting both the positive as well as the negative half cycle of the input, that is the AC input, to DC. So that is what a full wave rectifier is called as. Now full wave rectifier can be classified again into two types, that is it can be a controlled rectifier or it can be an uncontrolled rectifier. When we talk about controlled and uncontrolled, the difference is the power electronic switch which is used. In the case of an uncontrolled rectifier, we'll be using the diode. So if the diode is used, then it can be called as an uncontrolled rectifier. If we are using a switch which can be controlled, like a thyristor or SCR, or it can be a MOSFET, or it can be an IGBT. So such kind of rectifiers are called as controlled rectifiers. So here we can see that we are going to evaluate the operation of a controlled rectifier. Uncontrolled rectifier can be easily understood from that. So let's get on. So in order to consider the operation of a controlled rectifier, I'm going to consider a thyristor or an SCR. So we'll be drawing an SCR like this. So we'll make use of 4 such SCRs. So now we have a controlled rectifier which is drawn here. Here we can find that we have 4 SCRs that we have taken. So this I can call it as T1, this one I'll call as T2, this one I can call it as T3, and this one I can call it as T4. So here the input is a AC supply which is represented like this. So this would mean the input is a single phase 230 volt 50 Hertz AC supply, which is what we'll be getting at our plug points in our homes. So now I want to convert this AC, which will be an alternating current, which would be varying like this with a frequency of 50 Hertz. So this would mean we'll have a time period which we can calculate as 1 by F, which will be equal to 1 by 50, that is coming to be around 20 millisecond. So that means the total duration that we can take is 20 millisecond. The total duration will be 20 millisecond for one cycle. So that would in turn mean you can have, or the positive half cycle will be for 10 millisecond and the negative half cycle will be for 10 millisecond. So that is the duration that we are going to get. Okay, so now what we are going to do is we are going to analyze the polarity. Okay, so positive half cycle means we can see that it becomes positive in this side, right? So during positive half cycle, the positive is or the power supply or positiveness will be at the top end, right? And during negative half cycle, the positivity will be at the bottom end. Okay, so what we are going to represent here is we are going to show for the positive half cycle, the polarity will be positive and negative like this, okay, where we have positive at the top and negative at the bottom, while during negative half cycle, the polarity will be interchanged, that is, this will be positive and this will be negative. So this is for negative half cycle, the blue color one, and the red color one is for positive half cycle, representing the positive half cycle. Okay, now let us analyze how is the waveform going to be. Okay, so for that let me first draw the output waveform. So output we are going to expect across the load here, which is shown as a resistive load, that is the R value. Okay, so we'll have the output V0, we can call it as V0 coming across this. Okay, now how is this going to happen? Now during positive half cycle, what would happen? These are SCRs, and we have seen in the previous capsule that SCRs will get forward biased when we have a positive connected to its anode and a negative connected to its cathode. So this is its forward bias condition, and during this time only the conduction will happen. Okay, so here we can see when I'm having positive at the top and negative at the bottom, which all of these will become positive or forward bias. So we can see this positiveness will come here, and so T1 can be taken as a forward bias SCR, because positive will be coming to the anode here, right? This is anode, this is cathode, so it will be coming to the anode, so it will become forward biased. Okay, but when we consider the other one, next one, let us consider this one, T4. Okay, but T4 you can see positive is coming to its cathode, and its anode will be connected to negative, or its anode is at lower potential as compared to cathode. Positive is coming to cathode, so this is reverse biased, right? Then if we take T3 we can see the negative is coming here. Okay, so since negative is coming here, what would be at the anode? At the anode we'll have negative, right? So that means that is not proper, right? If it is negative, then it is reverse biased. So this is reverse biased. Okay, but when we come to T2, we can see that it is coming as negative on the cathode, right? So in that case, that becomes forward bias. So here we have T1 and T2 as forward biased. Okay, so if we trace the current path, we can see that the current will be flowing something like this. That is, it starts from the positive, from the supply, then it goes like this. T1 is forward bias, so it goes like this, right? Then it goes like this, then it gets into the load. Okay, then it comes here at this junction. It can either try going through T2 and T4, but T4 is reverse bias, so it will come like this. It will go through T2, right, and then it will come back to the source. Okay, so this is the path taken for the positive half cycle of the input. Now here you can see we have the load, and across the load the current direction will be downward, that is like this. Okay, current direction is like this, and the polarity developed will be plus minus V naught. Okay, so during positive half cycle I'll get an output which will be something like this. Okay, and that too for a duration of 10 millisecond. So this is the output that I'll be getting for the positive half cycle. Okay, now let us analyze for the negative half cycle. Okay, so during the negative half cycle we can see that the polarity interchanges. So here now this becomes positive and this becomes negative. So in that case, let us try to analyze what are the parameters that we are going to take. So in this case, this negative is connected to this point of the thyristor T1, that is the anode, and this is the cathode. Again, this is the anode, this is the cathode, this is the anode, and this is the cathode. So a quick examination of this will show us that which all will be forward biased. T1, is it forward biased? No, it is reverse biased, right? Same way we can see that T4 negative is coming to cathode, so that will make it forward biased, right? Then we can see that T2 negative is coming, positive is coming to cathode, so it will become reverse biased. Okay, while T3 we can see positive is coming to anode, so it becomes forward biased. So we have T3 and T4 forward biased. Now let us analyze the path flow of current. Okay, so it will be starting from positive, it will be going like this, it will be going like this, and then it reaches T3, right, and it goes through T3, and then it goes like this, it goes like this, it goes through this. T2 it cannot go because it is reverse biased. Then it goes through T4, right, and then it goes like this, it goes like this, and it reaches back. So here we can find that the current direction remains the same as in the positive half cycle, right, and the polarity will also remain the same. So output will get a positive half cycle like this, right, for 10 millisecond further. So this is actually the output that we'll be getting from a controlled rectifier. We can see that the input was varying between positive and negative half cycle, but in the output we have made it to be completely positive. This is called as an inverter operation. However, when we look at the waveform, we can see that the waveform is not a pure DC, right? This is right something like a pulsating DC because the output has lot of harmonics in it. Okay, that is AC components in it. So how do we eliminate this? We can eliminate this using some filters. So filters basically will be using something like a combination of LC filter, that is inductor and capacitor. So inductor and capacitor addition will help us to remove the ripples in voltage and current. Inductor will help to remove the ripples in current, and capacitor will help us to remove the ripples in voltage. So ultimately, when we apply a filter, we can convert it into a pure DC, which goes like this. So this is how the rectifier operates. Now, why is controlled rectifier required? So when we talk about controlled rectifier, we know that there is a gate available here which can be used to control the switching. Okay, the beauty of this controlled rectifier is I can control the output voltage to whatever value I want. Okay, if it was a diode, I'll only get the average voltage and I cannot change that. But in the case of a controlled rectifier, I can actually make this red line move up or move down based on the requirement. Okay, so what we do is we are going to control the gate in that case. Okay, so if I am assuming I am giving a controlling angle, this is known as firing angle. Okay, assume I am giving a firing angle of 18 degree. Okay, 18 degrees is the firing angle. That means I am going to give during the negative half cycle, or during the negative half cycle, this will consider since T3 and T4 are forward biased. So I'll give 18-degree firing angle to T3 and T4. Okay, what does this mean? Let us analyze. Here we can see that one cycle will be how much degree? One cycle will be from this point to this point, it is 180 degree, right? From 0 to 180 degree, and from here to here it will be 360 degree, right? So one cycle is equal to 360 degree. Now we know one cycle is equivalent to 20 millisecond. Right, so 20 millisecond is equal to 360 degree. That means 1 millisecond is equal to 360 degree divided by 20, that is equal to 18 degrees. Okay, so 1 millisecond is equivalent to 18 degrees. Okay, so if I want to control the voltage, I just need to control the degree, firing angle. Okay, this is known as alpha, is known as firing angle. Okay, so if I want to control the voltage, what will I do? I'll control the firing angle. I can bring, say now I am giving 18 degrees. So that means only after 1 millisecond, the triggering happens. Okay, so the waveform that we will be getting will be something like this. Okay, this portion will be eliminated. Okay, this portion will not be present, and the waveform will be something like this. So now you can see we have cut off this portion. This portion is cut off. So when we cut off that portion, basically we are actually reducing the average. Right. So when we cut off that portion, the average is going to lower down. So similar to this, we can control it for whatever value that we want just by controlling the triggering period or triggering time that we want. Okay, so now I have delayed it by 1 millisecond. I got a delay of 18 degree. Firing angle becomes 18 degree. Same way I can make it to 90 degree. If I want, I can make it to 90 degree. So then the waveform will be something like this. This portion will be completely eliminated, right? And then it will be starting only from here. So waveform will be looking something like this. That is, for positive half cycle, it will be something like this. Okay, and negative half cycle, again it will be something like this. So this advantage is present when we use controlled rectifier. In the case of uncontrolled rectifier, we cannot do this. Okay, we can have only the full half cycle or positive half cycle and negative half cycle as such. But this advantage is there in the case of a controlled rectifier. So this controlled rectifier can use any kind of switches. It can be MOSFET, it can be IGBT, it can be SCR based on the power application. Now let us try to analyze the simulative model. I am going to create a simulative model for this. For that, we'll just go to Google. Okay, we'll go to Google. So this is MATLAB online. We can try it on online. If you want to try, you can try out matlab.mathworks.com. Okay, matlab.mathworks.com. So when you click on that, you will have a window open like this. Okay, one thing is you will have to sign in. So here I have signed in, same way you will have to sign in. Okay, so you can create an account free and you can just sign into that. Okay, once you sign into that, you will get this page coming like this. Okay, so now what we are going to do, we are just going to replicate a experiment like that. So go to the first block here, Simulink, you can see. Okay, so we'll click on Simulink. So when we click on Simulink, you can see that a page like this comes. This is known as blank page. Create model. You can click on create model. That is blank model. You can click on create model. So when you click on create model, a new page will open. That is the Simulink workspace. So in that Simulink workspace, we are going to model the system. So here you can see the Simulink workspace is open. So I'll just enlarge it properly. So this is my Simulink workspace. Okay, so now we have to select all those things which is required. So let us see what all things do we want. We require something which is known as SCR. So how many SCRs do we want? We want 1, 2, 3, 4. So 4 SCRs should be there. One AC source should be there. One resistor should be there. And then maybe to monitor the waveforms, we'll have two scopes, that is to monitor the waveforms. Okay, so then we go to something which is known as library browser. Okay, so in the library browser, if I click on the library browser, we can see that we can open that and use. Now MATLAB is a very useful tool, and actually it is, since it is online, it is a free version, you can try it out, but this is a basic version, but it is very useful to simulate and study all these parameters. So here what I'm going to do is, I have the Simulink library browser, so I'm going to search for thyristor, Thyristor, thyristor. So if I click on thyristor and click on enter, so it will start searching. So you should have a stable internet connection for trying this out, because of course you are doing it on online, so you have to do that. Okay, so here you can see a lot of options are coming in, right? A lot of options are coming in, and here what you have to select is just go down, and as you go down, you can see there is something which is called as detailed thyristor, a black color one. Okay, so we'll just pull that onto the page. So you can just pull it, just drag it onto the page, or if that's not working, if it's taking time, you can right click on that and then add block to model untitled. So either way you can do that. So you can see it came here. Okay, so now I want 4 of these, right? So I can just do one thing. I'll click on this itself. Okay, I'll change its name. You can just double click on its name and type T1. So this is my T1. Okay, so I want it to be placed centrally. Okay, now I have to, okay, now I'll place it centrally. Now the orientation was something tilted, right? So I'm going to click on this, and you can click on Control R, so it will rotate. Online MATLAB, it might take some time, so what we do is we can either go to right click onto it, and you can see there is a rotate and flip. In that you can click on counterclockwise. So now you can see we have T1 here. Okay, so same way I'll be placing the other elements. So I can go to library browser again. I can get in T2, T3. Same way I can bring it here. This one I'll name it as T2, sorry, T4, and rotate it. Same way this one I can rename it as T2. And I can rotate it. So we have all the 4 SCRs ready. Okay, now next thing that I want is a voltage source. I'll check voltage source. So when we click on voltage source, you can see there are a lot of voltage sources coming in. Okay, so in this one, what we are going to do is we are going to select AC voltage source. So here you can see there is a black color thing. Okay, so I'm going to pull it onto the page. Or I can add it like this, add block to model untitled. So we have the voltage source coming in. So this is our input. So this is the voltage source that we are going to take. Okay, now the last thing that we want, or one more thing that we want, is the load. Okay, so what we search is we are going to search for RLC branch. Okay, RLC branch. So please use that terms so that we can find out what is the resistive component which is available. So RLC branch and search. So you can see there is a combination of different items there, but we are going to take this one, series RLC branch. So you can just pull it onto the page. Okay. Yeah, so that's the main things that we want. So I'll just rename this again. I'll click on the name. Okay, and rename it as load. Load. Okay, so again I'll rotate it so that orientation becomes proper. Okay, now just let us just connect it. So here, how did we connect? From this cathode, I'm connecting it to this point, right? Then from this anode, I'll connect it to this cathode. Okay, from this anode, I'll connect it to this cathode, this anode. Okay, and from this cathode, I'll connect it to this anode. Okay, and the AC source will be connecting in between, that is at this point. Okay, that is positive, and this point will be connecting the other end in the middle. Okay, and the load I'll connect it to the extremes, this point. Okay, and this one I'll connect it to this point. It's simple in connection. Okay, so now I want a load which is resistive in nature. So I'll double click on that, double click on this load. So you can see branch type will come. I'll select R. Okay, and let me take a resistance value of 10 ohm. Okay, so that is the resistance load. So you can see the figure has changed, become a pure resistive load. Okay, and if I go to the input, we can see we will double click on the AC voltage source. So we can see there is a various parameters given. Okay, so frequency we are going to take is 50 hertz. Okay, so when we look at the peak amplitude, we know that the voltage that we have to consider is 230 volt. Okay, now this 230 volt will give us a peak value. How much is the peak value? V peak will be equal to, this is VRMS voltage, this is RMS voltage. Okay, so that will be VRMS multiplied by root 2. So that is 230 root 2. So that is will be giving us around 325 volt. So the peak amplitude that we are going to enter here will be 325. So I'll rename this as 325. Okay, so that's it. So that is our source that we have. So now what is missing? Let us try to analyze what is missing here. What do we want to have more? Okay. Next thing that we want is we should be able to control these switches. Right. So for that we are going to search for a pulse generator. So we can just type in pulse generator. And you can see there is a pulse generator here. So I'll just pull it to the page, or I'll add it. Add block. So I have added the pulse generator here. Okay, so we can see how many pulse generators do we want. We want to operate T1 and T2 together, as you have seen, right? During positive half cycle, T1 and T2 are operating together, and during negative half cycle, T3 and T4 are operating together. Okay, so the thing is, you can see when T1 and T2 are on, then T3, T4 are off, right? And when T3, T4 are on, T1, T2 are off. So I just need a NOT gate maybe, right? So what I do is, first I'm going to connect this pulse generator to T1, and I'll connect this to T1, and I'll connect it to T2 because both of them require the same pulse. Okay, so connected it from pulse generator to T1 and T2. Okay, now what I do is I'll search for something which is known as a logical gate. Okay, so here you can see there is a logical operator. Okay, I'll just add that, and then you can see I got a logical operator. Okay, so this is what I'm going to use to connect to T3 and T4. So if you click on logical operator, double click on logical operator, you can see that you have various other options. That is, you can select or, nan, or, not, and all. So there is not here, so I'll be selecting not. Okay, so that just inverses whatever input is coming, it just inverses that. Okay, so I've connected it here. Now this NOT gate, I'm going to connect it to T3, and then I'll connect this one to T4 and T3. Okay, so now what did I do? When I get a signal, T1 and T2 will turn on while T3, T4 will turn off because it is a NOT gate, or the opposite. So that is how the connection is done. Okay, so now that is it. Now we'll have to have two more scopes to connect to input and output. So I'll be searching for something which is known as voltage measurement block. So that is like a voltmeter. Okay, when we talk about voltage measurement block, we'll be talking in terms of voltmeter, which is used to measure the or evaluate the voltage. So here you can see I have this voltage measurement block. I'll be pulling this to the page. So I have this. Okay, so then I'll be connecting the positive across the input, positive, and negative to the negative input. Okay, same way I want to visualize the output waveform also. Okay, so since I have to visualize the output waveform also, I'll be using one more voltage measurement block at the output. Okay, yeah, so I'll be bringing it to this point and I'll be connecting across the load. Okay, now to visualize everything we should have a scope. So I'll just search for a scope. So we can see this is the scope that we have. So I'll pull that scope onto the page. Okay, so now we have the scope as well. So that's it. That's the connections that we want. Okay, now I want to display both together. Okay, so what I'll do is I'll double click on the scope. Okay, and then I'll go to this configure parameters here. Okay, so I'll do one thing. First I'll click on the configure parameters. Okay, then you can see there will be a lot of displays coming here. So I'll just change this to 2. Okay, 2, and then click on layout. Okay, so that's it. We can actually visualize both. You can see here 2 inputs have come, so we can use that itself. So we'll be connecting the input and output source like this. So here the lower is the input source waveform, and the upper is the output source waveform. Okay, now there is one important parameter which is missing, which is known as a power GUI block. This is actually a graphic user interface which will be a communicating platform between the user as well as the software. So whatever we are telling, the interpretations will go only if the power GUI block is there inside the simulation model. So you have to search for this power GUI and bring it into the page. Then only it can work. Okay. Now the last step is we have to configure this pulse generator. So I'll click on the pulse generator. So if you open the pulse generator, you can see there are various parameters. So we're not going to change the time-based pulse type. This also simulation time, amplitude remains the same, but here time period changes. Okay, time period we have seen we are using a 50 hertz signal, right? So we are going to change this to the time period that we are going to take, that is 20 milliseconds. So this will be 20 e minus 3. That is what we are going to write, 20 e minus 3. Pulse width I'll make it to 50, and that's it. Only these two changes are required. Okay, so I'll apply, click on apply, and okay. So there you have the simulation model. Your stop time is 10. Okay, now what I'm going to do is I'm just going to run this. Okay, I'll just click on run. So now we can see the compiling is happening, and then the model is running. Yes, completed. Okay, so once the model is run, I'll just click on the scope. Okay, so here you can see this is the output that we are getting. So let us analyze what the output is. Okay, so what do we want? We want an input which is sine wave, and output which is a positive half cycle, or it has only positive half cycle. So what I do is I'm going to click on this zoom in option. Okay, and I'm going to select one particular region. Okay, I'm going to select one particular small region so that we can enlarge it and see. Okay, and I'll just leave it. So you can see the waveform that is coming. You can see that it is coming like this. Okay, it is operating like this, and you can see that the waveform is actually creating a half cycle. Okay, so I'll just enlarge it a bit more so that it can be more visible. Maybe one cycle I'll take. Okay, so this is one cycle. So you can see this is the negative half cycle of the input, blue color, and then it goes like this, positive half cycle of the input, and output you can see this yellow color, it is always positive. Okay, and let us just evaluate the time period. Okay, let us see what is the time period of one complete cycle. Yeah, so you can see it is starting at 1.420 here. Okay, and it is ending at 1.42, and this is 1.44. Okay, so it is ending at 1.44. So that is 1.42 to 1.44. The difference is 20 millisecond. Okay, so that is one cycle. And you can see the half cycle is also 1.42. It's starting and it reaches 1.43. So that is 10 millisecond. Again 1.43 to 1.44. That is 10 millisecond. So that's 20 millisecond. So that is how we simulate the rectifier operation using MATLAB. Okay, now we can also try to provide a delay. Okay, and let's see how that works. Okay, so here phase delay, how much can I give? We have seen that 1 millisecond is 18 degree. Okay, so assume I want 72 degree. Okay, so that would be maybe 4 millisecond. Okay, so 4e minus 3, that is the delay. So here you can see I have given the value as 4e minus 3 in phase delay. Okay, so if I just do that and apply and run it, let us see if it provides us a 72 degree phase delay. Okay, so now let us open the waveform again. Just that small change I have done. Okay, and let me enlarge this. Yeah, so you can see the waveform has changed, output waveform has changed because we have given a delay. Okay, so again I'll just select it for one cycle and see. See, you can see there is a change in the output waveform. Okay, this is because we have controlled the waveform, so this would make the average also go down. Okay, so similarly we can control based on the phase delay. I can control whatever value of delay that I want, and by that my average of output average value will also decrease or increase based on the value that I am selecting. So hope you understood this concept, hope you understood the operation of the rectifier, and hope you understood the simulative model of the rectifier using MATLAB. So that's it guys. Thank you for watching the video. If you like the video, please subscribe and join me for more exciting topics in this area. Thank you very much.